In? Oh, okay. All right. So let me begin by using this slideshow and to review and add some things to the coloring questions that I was talking about last time. And you may enjoy this Escher drawing, which perhaps has the first appearance that I know of the sign we've been using for virtual crossings. I see the circled crossing here in the diagram that this fellow has on the floor in front of him. And he is holding an impossible cube, which is diagrammed by his diagram, where he has indicated the impossibility of the embedding, the straight line embedding, to be of this particular form. So, in fact, there's a subject which we have not actually explored very much, although it has been explored a little, the relationship between diagrams with flat lines, straight lines, and the fact that they may not be realizable in three-dimensional space by straight sticks. And in fact, there is a little work on this sort of thing, mathematical work on this sort of thing, in the sense of finding least stick numbers and so on. But for the impossible ones, perhaps no real theory. The only theory I happen to know, I'm just chatting here, is also work by Penrose, where he has a paper about impossible figures where he uses check cohomology to measure them. So there are some virtual possibilities of a different kind that we haven't been actually looking at directly. Anyway, this is an Escher drawing. I should get the date of it because of the fact that it uses these virtual crossings. I'll try to do that. Now, can we use the slideshow? Right. So last time I was telling you about Penrose's ideas for studying coloring, and this is part of a famous paper of Penrose's, which you might look at if you haven't already, entitled Applications of Negative Dimensional Tensors. And the dimensions he refers to are the values of a closed loop. So we're very familiar with this from aspects of quantum topology, that we would have the trace function corresponding to a dimension. And we're also very familiar with this idea of tensor network, which he began, of taking an algebraic apparent tensor form. And like here we have theta upper AC lower F, and over here we have chi upper B lower DE G, and they are placed in this case with respect to a vertical line. And so we would be inclined to say, oh, well, over there on the left, it's an element of a tensor category, and it's being represented, it actually is represented into certain tensors. And I'm just showing you Penrose's writing about this. You see, he would use it. He used it all over his work. For example, he might have a metric tensor, and he would represent it by a cup or a cap. And he would want the upper one and the lower one to be inverses of one another, as is normal for a metric tensor with upper and lower indices, and that is consistent with having the cup and the cap cancel each other out. And he had a system which he called binars, which has the negative dimension of -2, and the sum of smoothings in two ways and a crossing is equal to 0. And from our vantage point, we understand this is a special case of the bracket, where the A in the bracket is -1 and the value of the loop is -2. And what Penrose had discovered was that that this was related to the structure of the group SL2 on the one hand. He wasn't thinking of knot theory, and he wasn't trying to put crossings over and under, but it became the underpinning of his theory of spin networks. And he used, I'm just showing you little excerpts from that paper on negative dimensional tensors, just to give you an idea of how much there is here. He, as I said last time, he works with I epsilon ABC, which he denotes by a little white circle at a trivalent vertex, and that epsilon is 1 or -1 or 0 according to whether the sign of the permutation ABC is 1 or -1, or 0 if A and BC is not a permutation, if there is some repetition in there. And then you have tensor networks with reductions that are available due to the identities about the epsilon and various evaluations, which you see here. The most telling of them, since we know from last time, but I'll remind you that this is going to calculate the number of colorings of a plane graph if you put in this tensor at every cubic vertex. It's going to calculate the number of edge colorings where there are 3 distinct colors coming together at every vertex. You might think, aha, now we'll solve the 4-color problem with these tensor networks, but there is a little clinker in there, and that clinker has to do with this minus sign right here when you have a pentagonal expansion, because it is the pentagon that gives all the difficulties in the usual ways of trying to do the coloring. But let's go on. This is his idea, indicated with his diagrams. In fact, here's a graph. I want to know how many colorings there are of this graph in the sense that I said before, 3 colors at a vertex and all distinct. And this, by his result, is precisely equal to the evaluation of the tensor network that I indicated. You put an I epsilon ABC at every vertex. That means you have variables for the edges, and you sum over all possible choices of those variables. That's the evaluation of the network. You sum over all possible choices from 1, 2, and 3. The only things that are left will be colorings, and each one will have I to some number, because it will be either I or minus I in its actual evaluation. So you're going to have plus or minus I, a product of them, and that product will in fact be equal to 1 for every coloring, and so it counts, and that's how it works. And here's an example. So at this point, we're reviewing what I did last time. Here's an epsilon tensor. Get something out of the way there. I'm using letters I, J, and K, and the order I to K to J counterclockwise, I, J, K, is what I call plus square root of -1, and I, J, K clockwise I call minus the square root of -1. And then you can look at that coloring. Here's a coloring, and it is a coloring, Kij, distinct at every vertex. And then at every node, you're getting either plus or minus the square root of -1. And then by some coincidence, which we want to remind you why it works, the product of all of them is equal to 1. It's a parity kind of consideration. And because these products will always be equal to 1, this tensor contraction network will count the number of colorings of the graph. So in order to understand how the count ends up being what it is, I am going to use a reformulation of what it means to color a graph in terms of 2 types of colored loops. One type of colored loop is a red loop, and the other type of loop is a blue loop. And I will regard the colors as named by red and blue and purple. That's the 3rd color. And that 3rd color will be thought of as factored into red and blue. If purple is factored into red and blue, then as you walk along a coloring, you can say, I'm going along red, but now I meet a vertex, and there will be 1 red in that vertex. other than this red, namely where purple is. And so I will go through purple and then I come back to red. And in general, this factorizes the coloring into a collection of loops that are interacting with one another at the purples. And so you see here in this simple coloring, we have one red loop and one blue loop that are touching along the edge that is called the purple. And I call such a factorization of a coloring a formation. And then you see that in these formations, of which I'm sure I have more complex examples in other slides, you'll see in a moment, these sharings can be of two types. I will just talk about a blue loop going through a red loop, but obviously it can also be a red loop going through a blue loop. Blue and red are the only colors that touch. Blue does not touch blue and red does not touch red. Blue can go along, share an edge, and go off on the opposite side of the red, or blue can go along, share an edge, and go off on the same side as the red. And those are the two kinds of interactions that are involved. So here would be a more complex formation for a coloring of a certain graph. And the thing you see is that, of course, you can draw infinitely many formations. You just draw some curves that are red and some curves that are blue that touch the red curves according to these rules. So a blue might touch a red and cross, or a blue might touch a red and decline to cross. And so we have two systems of curves like this. Each one, any one that you draw of the infinitely many, has an underlying graph, because as soon as you draw one of these, there is a trivalent graph that underlies it. And so the four color theorem reformulated for coloring, edge colorings of cubic maps, the four color theorem for that actually is stating that every graph has a formation if it's one connected, if it doesn't disconnect under the removal of an edge. Every one connected graph has a formation, and formations are prolix. So it turns the problem around a little bit, because you think, well, if I'm given a graph, maybe it's hard to find the coloring. Maybe it is. But if you're just generating colorings and you care to make drawings of this kind, why you find that you're generating all the graphs many times over. And perhaps you might think that would make the theorem obvious, but it doesn't. But it makes the evidence for the theorem very available. So here's another example, as I said. Here's a graph, here's a formation, and in this formation you see that you have same side interactions and crossing interactions, both of them in the corresponding formation. And I've indicated all the different aspects of that in this drawing. So, so then the other theorem that we talked about last time is the following statement, that if you have a plain cubic graph with no isthmus, one connected, no edge that disconnects it if you remove it, then there exists an even perfect matching of the graph. Now, the even perfect matching is in fact all the edges that are colored by one of the colors. You suppose you've colored it with three colors. Here I used ABC instead of P, Q, and R, but if I have any coloring of this, I can choose one of the colors. In this case, I've chosen C, and I have marked all of those edges. Well, those are disjoint from one another, because the next one over they're disjoint from one another. And so that forms the perfect matching. All the edges in the graph are taken up by a disjoint collection of choices of edges. And those are called the perfect matching edges. And the thing is that it's an even perfect matching in the following sense, that if you start walking on the perfect matching, avoiding the perfect matching edges, you will go through cycles. So for example, if I look here and walk without going through perfect matching edges, I have a little cycle up here. And it's even, you see. What happened there? That's interesting. Let's look at my diagram again. I chose the wrong one. The one with the C's is the one on the right. Yes, this is the one that corresponds to the C's. And now let's look at the walks that you could take along non-perfect matching edges here. I walk along, I'm walking, I'm walking. And I came back to where I started. And in fact, there was only one cycle, but there has to be a cycle. I walk on the edges from the graph obtained by deleting all of the perfect matching edges. Well, it's going to be even. Why is it going to be even? Because it's labeled by the other two colors, and you go along saying A, then B, then A. I'll do it here. A, then B, then A, then B, then A, then B, then A, then B. And finally, you get back to where you started. It's even. So a perfect matching is said to be even if the complement of that matching is a collection of even cycles. Now, it may be possible also to take your same graph and put down a perfect matching on it that's not even, and that's what I've indicated on the left. 1, 2, 3, you see. So this perfect matching is there, but it doesn't give us a coloring. Even perfect matchings are exactly colorings because you can take two of the colors and alternate them around the cycles in the complement of the perfect matching edges and use the third color for the perfect matching edges, and you're done. So another approach to understanding the coloring problem is to try to find all the even perfect matchings. Very interesting thing to try to do. Every cubic map with no isthmus has a perfect matching. That's proved by taught later and earlier, perhaps by, I think it's actually proved in that generality by Holton and Sheehan in their book Peterson Graph, but it goes back to Peterson. You'll find the general proof in that book on the Peterson graph. Here's the Peterson graph. Here's the perfect matching for the Peterson graph. But the Peterson graph is uncolorable, and the complement of the perfect matching, as you see, have 5 cycles in it. And there is no perfect matching of the Peterson graph that's even, as you could find if you start playing around with it. So there's an uncolorable that's not planar. And planar uncolorables have to have an isthmus, and they are, examples are like this one here, certainly uncolorable, and this one, and so on. So we're interested in thinking about the structure of a coloring. And now I'm saying something that I didn't say before. Here's a perfect matching site. And I can say of that for my coloring that the coloring might be such that this color and this color are the same, or that this color and this color are the same. Or that it crosses over, that this color is the same as this one and this one is the same as that one. And then you see that you can classify things in those terms as well. So that, for example, if I said I will consider trying to color this in such a way that these all follow this pattern, well, I can't do it, because if I say that parallel lines locally will all be colored differently, which is what has to happen, same color, different color, different color. If that happened, well, then I would be trying to color this loop of one color, no light, no dice. But if I switch some of them, and in this case I switch the requirement here and the requirement here, now I have 2 loops which are asking to be colored differently, and when they are colored differently, the local criterion is still satisfied, and I get a coloring. And as you see, when that happens, I will get a formation where I have a same side interaction in the places where I have the parallel, and a crossing interaction where I have the crossing. And so you can think of the coloring problem in terms of setting the problem like this, that these should be different, and then switching some of these until it really works. And so the four-color theorem says that you can put down some loops in the plane, like a state of the bracket polynomial, and then ask whether you can switch them in such a way that it's colorable with three colors using those loops. Colorable with two colors, because the third color is going to be at the interaction points. You can try to do that, and it works. But the mystery is, why does it work in the plane? So for example, here's a nice example of this. I write down a state like that. I write down any planar state, bracket type state, and I ask that these should be different, but I'm allowed to switch. Switching means that I'm allowed to replace a smoothing like this by a crossing. That's the game. I'm not doing knot theory yet. I'm just playing a combinatorialist game, but using state diagrams for knots. All right, so here's one, and here's another. This one's not planar, has some immersions in it, immersion crossings in it. Aha. Well, the one on the left is colorable. It isn't colorable as it stands because we're supposed to use colors so that out of the three colors, these should be different. And that's my criterion. And I have three colors to choose from. These will, if I do it that way, then I can just consider it to be any coloring at all. These do not have to be the perfect matching edges. So I'm looking for three colors. That this color is different from this color. It's different from this color. So all three of these in the middle are different from one another. And then the outer loop must be different from them. Well, that required four. So this one won't work. There's no way to solve the problem. But if switching, then I might be able to solve the problem. And in fact, I can. And you might jot this down, but I probably will solve it in the next slide. Maybe it's too quick to ask you to do it. There are 1, 2, 3, 4, 5, 6 of these. So there are 2 to the 6th possibilities here. That's 64 possibilities. Of course, the symmetry cuts it back. And it turns out that only one of them manages to color. The one that manages to color is which one? This one is uncolorable. Well, here's the answer. Too quick. I switch them all. And when I switch them all, I have three loops instead of four. And I can color one red, one purple, and one blue. And I end up with a coloring. And you will notice that in the coloring that I chose, these edges here end up being different colors because I'm choosing red here and purple here. And so the interaction edge that comes about by compressing this back is going to be blue. And over here, I have blue and purple, and the interaction edge will be red. So this is not producing the perfect matching. It's just producing the coloring. And this formulation of the coloring theorem is you take a bunch of curves, a bracket state in the plane, and you put down the smoothings at the sites, and you say these shall not be colored the same. And then the four-color theorem says you can switch some of them, and it will be colorable if you're planar. And if you're not planar, well, how do you know this is uncolorable? You could enumerate everything, but actually this one that I drew here that goes out of the plane and is uncolorable is a special case of a general construction due to Rufus Isaacs, which is explained in a paper by him. If you're interested in the paper, I'll get it for you. It was a beautiful paper written a long time ago. But Isaacs had the following idea. Make this little gadget. this little gadget we will call Isaac's J. And as you see, it's got a non-planar crossing in it. Of course, it could be removed in some cases, but in some cases it cannot. And what I have done here is I have plugged 3 Isaac's J's together in a cycle. Isaac's J plugged into an Isaac's J, plugged into an Isaac's J, plugged into an Isaac's J. And then what Isaac's proves, and you can prove too if you want to do it without looking it up, is that if you plug an odd number of Isaac's J's together in a cycle, you'll get an uncolorable graph. So that means you can make infinitely many non-planar, uncolorable graphs in this fashion. And this Isaac's J is in fact a relative of the Peterson graph. If you collapse this 3 cycle in the middle to a point, you get the Peterson. Nice examples. The examples show that when you go off the plane, you can have uncolorables, and everyone's intuition before people ended up getting some kind of proofs of the 4-color theorem was Tutt's conjecture that any non-colorable, non-planar will have minors that are equal to the Peterson, which means that some collapsing will get you the Peterson, just like a collapsing of edges here gets you the Peterson. So that the Peterson phenomenon of being uncolorable is basically the only thing. Or another way of putting it is the Isaac's phenomenon is essentially the only thing that forces non-colorability. So, so this method that I just showed you, the logical expansion, is similar to the Penrose formula, but more general. I say that if you want to color a trivalent graph, you can say, all right, I will put a picture of it in front of me so that I have the cyclic orders here, draw it in the plane with immersion crossings. And then I will expand it, saying that this expansion means that the set of colorings of this is equal to the set of colorings of this plus the set of colorings of this. And that's because you could have colors here, red, blue, purple in the middle, blue, red, which would be this case, or red, blue at the bottom, and purple in the middle, which would be this case. Those are the only cases when I'm speaking of 2 different and 1 in the middle that's different from them. And so you can run this expansion and then keep track of what goes on while you do the expansion and work out the number of colorings. So for example, for the ktrt graph, which is this one, a box and another line up here, 3 parallel lines and a twist. It's called the ktrt by graph theorists. You can expand it and then think about counting what you got when you expanded it. And after a little while, work out that it has 12 colorings. On the other hand, if you do Peterson, and this is telling, watch what happens when you do Peterson. Notice that this formula I'm talking about is harder to evaluate than the original Penrose that we talked about last time. You have to look at the graphs that you got, but it's general. It will let you find the number of colorings and, in fact, the colorings of any graph by just taking an immersion picture of it. So if we take the Peterson, this is the Peterson, another exercise for you if you hadn't tried it. I told you the Peterson a little bit ago by saying it was a pentagonal pattern and another pentagonal pattern connected up with one another. But here it looks like a Mobius strip, but they're isomorphic graphs. Well, we expand on this edge and we take the crossing expansion on this edge. And then you ask yourself, well, what happened here? We have this little box here and 2 arcs coming out of the sides of the box that are told to be different. This crossing now means nothing. It's just this arc has to be colored differently from this arc. And over here, you have an arc coming out of the bottom of the box and another arc coming out of the top of the box, and they're told to be different. So we're getting 2 copies of this problem. Both of these problems are the same as this problem. And then you check, that there aren't any colorings of this problem. That you can just check directly. This problem says, try to color this graph. You'll find you can, but it will always happen that the left arc has the same color as the right arc. We leave you to check it by working it out. So this expansion is quite useful for thinking about coloring. Hopefully it's more useful than I know. Okay. Now getting over to the Penrose formula that we were talking about last time. The point being that when you have the bounce or the cross, you can think of the eyes that correspond to them in a coloring as paired. So we have a pair of I and minus I when it bounces, and we have a pair of I and I, or minus I and minus I, when it crosses, as you can see from the cyclic orders. That means that this pairing will produce a +1. You can ignore the bounces. This pairing will produce a -1 in either case. And that means that in a formation, maybe there's a drawing. Yeah, well, here's a formation. In a formation, you can redraw the formation in your mind's eye, saying bounces I'll ignore, crossings I'll think of as crossings. And then you have a picture of two Jordan curves in the plane, in this case, that are crossing one another. And they have to cross each other an even number of times because we're in the plane, and that's the point of the plane. Since two Jordan curves, any two Jordan curves will cross one another in an even number of points, and -1 to an even number is +1, every coloring will contribute a +1, and the Penrose formula is proved. So we have the Penrose formula. This identity can be thought of as the epsilon version of the general tautological expansion that I told you before, but it also is a consequence of the identity about the tensors. And we have this, and we talked about this before. We have that the value of a loop is 3, and so we have a skein type expansion, which will count the number of colorings of a planar graph. Having this, you can forget about the tensors completely. You can even forget about the formations, although you probably shouldn't, and just go ahead and count the number of colorings of a planar graph by this skein relation. Last time, I also talked about diagrammatic tensors, and I think I will just skip this. However, it is related. The fact that the cross product is supported by the epsilon tensor is related to the following reformulation of the coloring theorem. So I'm going to slow down and say this. I'm now switching context. I'm just going back to the coloring theorem itself. The map coloring theorem, four-color theorem, is equivalent to the statement that two associated expressions in the vector cross product algebra have evaluations using I, J, and K that are non-zero and equal to one another. So I write A cross B cross C cross D, or I write A cross B cross C cross D. I'm looking for a solution to this equality such that A, B, C, and D are taken from I, J, and K, and I, J, and K are the generators of the vector cross product algebra, the Lie algebra of SO3. I cross J is K, J cross I is -K, I cross I is 0. So a formula like this could become 0 sometimes because you might have J, K giving you I, and then crossing with I would give you 0, right? So we're assuming that we find some product of these which is non-zero, and then non-zero on the right. And if you can prove that you can always do that, that's equivalent to the four-color theorem. And the reason why is because you can interpret the vector cross product in terms of graphs. It's because you can think of A cross B giving rise to the cross product as the coloring of a little trivalent vertex, just like that. And I won't go into the details of this, but I do want to mention one other thing about this theorem. Other than that, you look at it and you think, well, so there should be some Lie algebra fact that will prove the four-color theorem. There should be. What fact? But there is a Lie algebra fact that helps us understand something here. Suppose I'm facing this algebra problem. And suppose I have found A, B, C, and D so that this cross product is non-zero. Well, if it's non-zero, it might as well have been in the quaternions, because the difference between the quaternions and the vector cross product algebra is in the squares of the elements. And if no square of anybody occurred here, you could say that this was a quaternion product. But the quaternions are associative, and therefore it will be equal to this quaternion product. Because of associativity. As long as this right-hand quaternion product is also non-zero. Because if in this quaternion product you add an I cross I, in the quaternions, it would be a -1, and that wouldn't be what you wanted here, because you want I times I to be equal to 0 for vector cross product. So what you need is that your product is non-zero for the left one, and also non-zero for the right one, and then they're necessarily equal to one another. So that's the beginning of a step in the right direction, you see? Instead of just saying that I need solutions, I'm saying all I need is to find it non-zero and to find the other one non-zero. Then I'm good because of the quaternions are associative. So it's subtleties of the algebra like that, the fact that the quaternions are associative, that will get you in the direction of the coloring theorem, but there is some subtlety of the algebra that seems to be missing. So how would I solve such a problem? Well, I draw a graph. That's all I do. I draw a graph making a tree out of this one and a graph making a tree out of this one. And I tie the two trees together and color it using graphs instead of using algebra. But that doesn't help it as a method of proof. Anyway, this is an elegant reformulation of the four-color theorem. Now getting back to Penrose's formula. Penrose's formula, as it stands, does not work for non-planar graphs. Why? Well, let's look at an example. Here is the K33, and we expand by Penrose, see that minus sign. Now it's similar to what we said before. However Penrose would evaluate this self-crossing doesn't matter, the way you would do it with Penrose formula, and you get the evaluation of this box with arcs on the sides. But over here, you have an arc going here and another arc going here, and so it's the evaluation of the box with the arcs on the tops. But those are obviously the same, and we're taking the difference, and we get 0. So it's an interesting problem to revise the Penrose formula so that you could get a count of the number of colorings by drawing the non-planar graph in the plane and adding a tensor for the virtual crossings that you get. So you will get immersion crossings. Think of them as virtual crossings. And then what is missing? Well, whenever we had a crossing in coloring, you see, the virtual crossing allows a coloring that's only one way to color. You can color this equal to that and this equal to that in your virtual crossing. But then when you get the colored loops, when you get the formations, you will find that you are getting some places where something crosses over and it's not being counted. So so those signs are going to go haywire. You won't get some colorings can have a minus sign if you have crossings in the graph. because you're not counting all the crossings between the colored loops. So therefore, the new tensor says I am +1 if these colors are equal, so that I don't care whether it's crossing or not. It's a self-crossing of a loop. But it's -1 if they're not equal. That's the new tensor. And you add that tensor into the situation. You can also write it as the difference between another tensor and an ordinary crossover, which is always 1, by saying that this will be 0 unless they're all equal. That's just a nicety for calculation, but you add a new tensor, and having added the new tensor in this way, you get a generalized Penrose formula that will count colorings of anybody. And then you can go ahead and use it. I won't do calculations, but I just will show you that it behaves nicely with respect to moving it around. So it behaves like a virtual crossing should. If you calculate the ktrt and keep track, then you don't throw this away except when it's a self-crossing. And you get down to cases near the end where you have to keep your track of the counts because you have two different circles that are crossing one another. And then the count will come out correct and you'll get 12. So the general case of coloring any graph whatsoever is solved by adding a tensor and putting the graph into the plane, immersing it into the plane, and evaluating it by the Penrose method. And so that is interesting, needs more study, obviously. That's the summary of this from last time, telling you a bit more. And now I'm going to shift and actually tell you a little bit more about coloring, and then we'll shift to the topology part. But now let's look at this. Now I am, sorry. There we go. Now I'm reviewing again the matter of formation and graph, right? Here's a formation. I drew it. I just drew a formation. And then I take the corresponding graph and find that I've colored this graph. Or perhaps you searched for coloring of this graph, drew it, and then drew the corresponding formation. The four-color theorem says that every one-connected planar G can be formated. Now I'm going to do a little counting about these formations. I'm going to count the number of red loops, the number of blue loops, and the number of alternating loops, which are the number of loops in the complement of the perfect matching. So I go along red, blue, red, blue, red. That's one. And I go along blue, red, blue, red, blue, red. That's the other. So there are two alternating loops. I count them. Those, in fact, are the total count of the number of alternating loop pathways in the original one, because when I do red, I'm actually doing red-purple, and when I do blue, I'm doing blue-purple, and when I'm doing the alternating, I'm doing red-blue. But from the point of view of choosing our coordinatization in red and blue, I'm counting red and blue and alternating. There are 6 of them in this one. There's a parity result. You can take your formation and you can take a loop in the formation, any loop like this red loop, and you can superimpose on that red either a blue or a purple of the other color. In this case, I've superimposed purple. And then look at this as a mod 2 cycle addition. Blue with blue will cancel. And then you get a new formation as a result. So in other words, what I'm doing is I'm taking this loop and I'm flipping the colors along the loop. Red becomes purple and purple becomes red. That's what happened. That's another way of saying what I did. I think of it as an operation on the loop by another color. So you can, that's called a simple operation on a loop. You can operate on red, you can operate on blue, and you can operate on alternating. If you have an alternating curve, you put purple on it and it flips red with blue in the alternator. Okay, now here's the parity lemma, which in another language is due to Tut, and in this language is due to G. Spencer Brown. Parity of this count is preserved under simple operations. So for example, we had 6 here, and I did an operation here which caused the 2 blues to become 1, and there's still only 1 alternator. Is it true? I'm walking the alternator. Yep. So there's 1 alternator, 1 blue, 1 red, and the number of loops went down to 4, from 6 to 4. The parity is preserved. If it's even, it's even. If it's odd, it's odd. You may find it interesting to prove that for yourself. I'm not making proofs at this point. So that's the parity lemma. And you can use the parity lemma to recolor some things. The way you, I'll show you an example and then we'll quit this combinatorial side. Every cubic map has small regions, follows from Euler's formula. Every cubic map has 2, 3, 4, and 5-sided regions. It's not hard to see, and I'm going to skip the slides that I drew, that if you're colored up to through 2, 3, or 4, and you want to extend over 5 over that, you can do the extension. But 5 presents a problem. In the original paper by Kemp in the 1860s, he showed a very clever way to extend over 4. And he said it works the same way for 5, but unfortunately it doesn't, and that was discovered by Haywood 10 years later, and then the problem became very public for a long time. I just point to this in my slide. Suppose I had a map that was all colored except for this region, and I wanted to color it. Kemp had a beautiful idea. He says, well, there are 2 different colors this way, and there are 2 different colors this way, because you can't solve it. And so what if you start switching purple to white? Well, then there might be a white that has to be switched to purple. And this might snap back into a chain of regions going all the way around from here to here. And then you wouldn't have done anything. Purple would have turned into white, but this white would have turned into purple. Oh, but this chain of regions, which goes all the way around, protects the switching from red to meet the blue and switch it out. So you will be able to switch the red to blue, causing some other regions to change, but it's protected by the purple-white ring that is going around, and the blue will be remaining there, and this will turn into blue, and now you can put a red in here. That was his argument, and that was the place where he said, well, it's the same for the 5-sided region, but it isn't. There is technique here for handling 5-sided regions in the class, in the category of formations. And I just want to give you a hint about how the parity result that I just told you is related to doing that. I'm going to solve a specific 5-region problem and indicate a general method in so doing. So I have this, and I would like to get an extension of the formation so that these become edges in the formation. But this doesn't work here in any obvious way because I have 3 colors on this region, you see. I have 3 already. I have purple, I have blue, and I have red. So if I were to, for example, draw in red around this, I would cancel that red. If I draw in blue around this, I would cancel this blue. And if I drew in purple around this, I would cancel the purple. So no simple drawing of a loop will recolor it. What I'm going to do is a parity changing operation, and this kind of operation can be systematized and proved to always change parity. I'm going to go halfway around. I'm going to go along the red loop all the way until I get to this edge here, cancel this edge, go back, and so I end up using half of the red loop. I use half of the red loop, cancel one of the blues, and then put in an edge here and come back round. And I'm doing it in blue. So now that means that this is the only cancellation that happens because I'm going along red and blue, except for the one place where I transgressed across the blue. So I do this operation. The operation will give me a new formation and a new problem because the missing edge is now here. The missing edge is over here. I get a new formation. That's the parity shifting operation, and you see it did shift the parity. We went from 3 to 4, if you count the loops. And 3 is the very least. So this is an example of a slightly hard problem in that I have the least number of loops possible, and it's going to give me difficulties in trying to recolor it because it's least. But here, because the parity shifted, it had to go up, and I have an extra loop. And this extra loop then can be used to affect the recoloring by doing some more work, which I'm not going to do drawings for. If I operate on this blue, I will break this red here and here, and I'll get 2 red loops, one down here and another one up there. And the fact that I can break this red loop away from the top means that I can then change its color, and I can end up with only 2 colors going around this region. And once I have only 2 colors going around this region, imagine that red has been eliminated, then I could draw in red and fill it in and get the extension that I wanted. This is the kind of operation on 5-sided regions that Spencer Brown systematized. He has a completely systematic way to deal with 5-sided regions, which, if you do examples, always solves them. I don't know a proof that it always solves them, but it deserves more work, deserves more understanding. And as you see, the entire arena here is filled with matters of parity that are subtle. The fact that parity is preserved is key, and the fact that parity can be changed under certain circumstances is also key. So that's some of the things that I know and am interested in about the trivalent coloring problem. Now, if we have a little more time, how much time do we have?
I think it's up to you. I think it's up to you. Well,
okay. All right. I'll take another 20 minutes or so, I think. Let's now look at going to virtual knot theory in relation to this. So these slides contain some of the same information that I was just telling you. So I'm skipping it, but now I get to this. Here's the transition point where when we ask this question, we're going to find things turning into knot theory. Suppose I said, well, here's the Penrose formula, and the value of the loop is 3 in the Penrose formula. What if I made the value of the loop delta? Do I get a new polynomial, like the chromatic polynomial? When you generalize to an arbitrary variable in the chromatic polynomial, you know, it works fine, but what happens here? So we take, for the sake of looking at the problem, let's look at what happens when I just leave the coefficients in the skein expansion the same, plus minus, and I evaluate by delta, the loop. Then, of course, you can see that you get delta minus 1 here. Why? Because I think we had it back here. If you're going to evaluate a little bloop, think of doing it with 3. You evaluate the bloop, you smooth it this way or you cross. This one gives you 3 times that minus 1 times this gives you 2. if this had been a delta, then you get delta minus 1, which is what I was saying. So you see that you will get delta minus 1 when you have this. So now look at this. Here's the thing. If I choose a perfect matching, then I can go ahead and expand this polynomial in a well-defined way from the perfect matching, because I just go ahead and expand each one of these according to the rule, and I will get a definite result. It's just a state sum. So if you choose a perfect matching, then you will get delta minus 1 from this one, and then I'm using this one, and I get a delta minus 1 squared and a delta. So that's what I get for my evaluation of this one. Now, what if I take this perfect matching, the other perfect matching for this little graph, and I expand it? And I find that I get 2 times delta minus 1 times delta. Now, certainly at 3, you have the nice fact that 3 minus 1 squared is 12, and 2 times 3 minus 1 times 3 is also 12. But in general, delta minus 1 squared delta is not equal to 2 times delta minus 1 times delta. And except for the trivial cases where delta is equal to 1, we conclude that delta would have to be equal to 3. And so the only case where this is going to be independent of the choice of perfect matching is when delta is equal to 3. But if delta is not equal to 3, then we have a well-defined polynomial in delta defined for any perfect matching choice on the graph. So we have a perfect matching polynomial. Now I'm going to skip this remarks about virtuality. I could do it in more general case. I can say that given a graph, given a trivalent graph, I can define a perfect matching polynomial. I will take A times the one way of smoothing the perfect matching edge, and the cross way of smoothing a perfect matching edge, I'll get a B, and I'll have a delta for the value of the loop, and this can be used as a graph polynomial to discriminate different perfect matchings of the graph. And what I'm going to do in the unoriented case is I'm going to map, I'm going to show you that what we're really looking at is the graphical bracket polynomial all over again from this point of view. So if I take, I'm going to map a perfect matching edge over to a virtual, small virtual tangle over here. And in order for this to be well defined, I need that it doesn't matter whether I put the virtual crossing to the right or to the left. And so I'm actually mapping to virtual knot theory modulo that replacement of simple flight replacement, which we've called Z-move. And bracket polynomial is well defined in that category because it doesn't matter which way you do that, as you know already, I'm sure. So when I wrote in these slides VKT, I meant VKT modulo that simple flight. And now notice what will happen. This will map to that, but then this with a virtual crossing on it will map to this. And you need to assume that in the graphs, it's also the case that you can flight the virtual crossing. So we're going to work in virtual crossing graphs modulo the Z flight. So that's what I'm saying here, that I'm going to assume that this is the case, and this is the case. If I work in an oriented category, then I don't have to worry about that. This is the equivalence in the virtual category, and in the virtual knot category, I'm going to work in virtual knots modulo this, work on oriented. So then the bracket polynomial, the usual bracket polynomial, doesn't see this, so that's fine. If we're oriented, I won't do oriented. So now look at what happened here. If I associate this to this, then let's just walk from knot theory into graph theory and back. I take a knot theoretic crossing. It's equal to this graphical crossing by my association, by definition. And then this expands A times this and B times this. And now the virtual crossings go away and you see you have the bracket. And the value of the loop is D. So that's what I mean, that the translation of the perfect matching polynomial, which has its own interest in the graph theory category, over into the knot diagrams is precisely the diagrammatic bracket. And so this means that we have a translation going back and forth between virtual knot theory on the one hand and graphs that have perfect matchings on the other hand. So a graph with perfect matching is an analog of a virtual knot and vice versa. And since the bracket polynomial can be specialized with a b equal to a inverse and d its usual value to be invariant under Rademacher moves, that means that there's a slew of moves on the graphs under which certain perfect matching polynomials will be invariant, among other translations back and forth. So we could consider the special case of the perfect matching polynomial for the bracket substitution and corresponding Jones polynomial. So you can ask, well, what do the moves look like? And they're pleasant enough on the graphs. Let's look at, for example, a 2 move. And you see that the 2 move looks like this when you translate it. And the 3 move is easier to look at because in the 3 move, all of the extra perfect matching edges are in the same places, can be put in the same places. So what you're seeing is the underlying permutation graph with some markings on it. So the moves in the graph category are reasonable moves to consider in the graph category. And so one can work back and forth between the virtual knot theory and the graph category. And I don't want to worry you about special evaluations that go back and forth, but I do want to show you an example or two. Let's see. Here's an example. Here's a well-known virtual knot. And we translate it in that way over to a graph, and we can flipe the graph a little bit and simplify it, and we end up with this perfect matching graph. And on the other hand, if you took the mirror image of that knot and you went over and examined the graph that you got, you would get this graph. And then the two polynomials are different, and that means that these are distinct perfect matching graphs. You're not going to be able, in the graph category, to get from this graph to this graph by the extra, including the extra Rademacher moves and so on. You won't be able to get from one to the other. And so statements that we're used to in topology about the virtual knots turn into certain statements about the availability of one graph, one perfect matching to be transformed into another. Let's look at another example or two, and then we can call it a day. I just wanted to give you the idea of the translation. You can continue this translation in various ways. So, for example, Scott Baldridge originally had thought about the perfect matching polynomial, not necessarily understanding that it was directly a bracket polynomial, but understanding that it was analogous to it, and wrote down in the graph category a Kauffman homology theory. We can say in these terms that Kauffman homology theory is morally the same as taking the graph, pushing it into the virtual category, and then taking the Kauffman homology over there. And we're still investigating that question, that idea. But there are lots of more direct, simple correspondences that you can look at. So for example, the trefoil knot, here's the trefoil knot, here's its image in the virtual category, I mean the graph category, excuse me. And then after a little simplification, we see that it turns out to be K33. A certain perfect matching on K33, not any perfect matching on K33. So, so that's the curious thing. When you're looking at it in the things in the graph category, you find a graph and you have chosen a perfect matching. That choice of perfect matching is going to correspond to some particular choice of virtual link. That means that if you just had a graph, there would be a collection of virtual links that correspond to its different perfect matching. And so you have a little bit of knot theory of a certain collection of virtual links that corresponds to the study of a given graph. Here's an observation. If you take your knot and make all the crossings virtual, this is exactly the same as removing all the perfect matching edges because of the way we map them. You see, you put in a virtual crossing. If you remove the perfect matching edge, then you just have the crossing. So if you make, so if you want to know, for example, is it an even perfect matching, then the answer over here is there should be an even number of components. So a classical knot or a link diagram, then if you start with a classical knot or link diagram, then you will get an even perfect matching. And so the corresponding graph will be three-colorable. Another proposition is that if you have a virtual trivalent with a perfect matching, it's got some virtual crossings in it, and a single circuit in the complement of the matching edges, then GM is an even perfect matching, and so it will be three-colorable. And the proof of this is, again, by that same translation. I think, in the interest of time, I shouldn't bother you about this other than state the result. Let K be any virtual knot diagram, one component virtual knot diagram. Then the corresponding graph is a three-colorable trivalent graph. So you see, the point being that one can try to get statements going back and forth across the boundary between the graph theory and the knot theory that inform the three-coloring problem, or one can try to take topological problems and translate them into problems about the graphs, or vice versa. We haven't done everything here. There is a paper or two by us, but this is still in the beginning stages. I'm not going to do this calculation. And I'm just looking at examples that would be worth. Right. So you can make various remarks to yourself as you explore this. Suppose you have a graph that's colorable. Then it has an even perfect matching. So here's a colorable graph. Here's an even perfect matching. Is this even? 1, 2, 3, 4, 5, 6. Yes. So then you can go over here and you'll get an even virtual link diagram in the sense that there will be an even number of it will be even in the sense that I mentioned before. And the four-color theorem asserts the colorability of trivalent graphs. From a given perfect matching of a graph, you can obtain other ones by switching cycles. And then you will get other links. So there is this question of what's going on among the links in relation to the colorings and vice versa. I'm repeating here some things that I already talked about, and then there are other directions, but I should just stop at this point. You see, what I'm saying is that it's not just the local combinatorics or translating invariants back and forth, but global things like covariant homology are also translating back and forth. You could define the covariant homology of a graph in this category to be the covariant homology of the corresponding virtual link. And this also provides a little extra motivation for understanding better covariant homology for virtual links, of which there is more than one candidate. There is the one originated by Vasily Manturov, and there are some others as well. So I'll stop here. And as you see, this is a very unfinished subject, which deserves lots more thought.
Well, as usual, we're very happy with this talk. It's a brilliant talk. Well, I wrote some questions on the chat line, but of course, this is very far from what I could have written. So maybe you can look at them.
Yeah, let's look at them for a moment. How to categorify the number of colorings? Well, in a way, having covariant homology is an answer to categorifying the whole thing, but maybe number of colorings should be thought of in and of itself as something to be categorified, right? That's what you're saying.
Yeah, that's what I'm saying.
We could look at the whole categorification that we have. We'll use your covariant homology and then ask, well, does that up level the number to something else?
Okay.
I guess I have another thought there, because we up leveled the, no, that's enough said, right? Yeah. We should have tensors having pictorial dimensions. Oh, you mean, yes, you mean instead of evaluating it as a number or a bit of algebra, just let it be the diagram itself.
Yes, exactly.
Yeah, right. In fact, maybe a place to look there would be to, say, begin with something that does have pictures like the parity bracket, since we're playing with the bracket. Why not look at the parity bracket and take it back over into the graph theory and back and forth and see what it's doing? You can follow that idea.
Okay.
Yeah. It would be nice to have dodecahedron colorings.
Where dodecahedron is a number.
Right. Right. Mm-hmm.
I mean, there should be some rules which evaluate something, but sometimes we are unable to evaluate, and once we are unable to evaluate, we can say that we end up with having something like dodecahedron, and this can be thought as a coloring for something, maybe for some colorant.
Here's an obvious project. Suppose we take our work on the Kuperberg spiders.
Yeah.
Right. There we have something very analogous to the Penrose expansion, but in virtual knot theory, we're going to graphs. We're not going all the way down to evaluations. That was the whole point of that project. So we have pictures there, but it's close enough so that we can also say we'll take the Kuperberg bracket for virtuals and pull it back over into the graphs and back and forth. So, so there is an example where we can examine how the picture work is going to interplay with the graph theory. That's a doable project. We have to think about it.
I enjoyed the talk.
There are a lot of doable projects here, you see, because what I'm setting up is a translation conduit. I should say also, it was an interesting surprise to me that the bracket polynomial came back out of the Penrose expansion that way, because, as I was saying at the beginning of the talk, originally we understood many years ago that the bracket polynomial was related to the binary calculus. So the bracket polynomial is related to more than one thing of Penrose's by dint of different ways of translation. And so I think we haven't figured out what's going on here yet.
Thank you. Thank you. It was great. Any further questions or comments? Well, everything is recorded, and you're welcome to write by email, and it would be great to continue conversations in whatever form. I'm really very happy with those talks. Thank you very much, Lou, and we will keep in touch on that as well.
Okay, thank you, Vasily.
Bye.
Bye now.